so in this video, I want to talk about the properties conductors have when they're in electrostatic equilibrium. But first, I want to remind you about what conductors are. Conductors are materials that have charges that can move. So the charges can move when you're in a conductor. And how this happens is like any other material. You've got an atom which has a positive proton and maybe some neutrons inside the nucleus, and then negative electrons going around the outside. But in a conductor, this electron can choose to leave its atom. So it could be like, nope, I want to take off and come over here. So a negative electron is moved, but it's left a positive nucleus. And so effectively, it can kind of look like you might have positive charges moving, even though it's just the electrons that are moving. How would this happen? Well, so say this electron takes off. And then there's a neighboring atom here with its nucleus and electron. And this electron says, oh, I'm going to hop over here to this atom and leave here. And that kind of looks like the positive charge moved this way, because of course, once these guys are paired up, they cancel out and you can't see them. So even though it's the electrons, the free electrons that are moving, it can appear that positive charges also move inside conductors. All right, so conductors, charges can move. When they're in electrostatic equilibrium, the charges aren't moving. Because static means, remember, still. So this is a situation where the charges are able to move, but they're not moving. So that must mean that the situation is such that the charges don't feel any force causing them to move if they're still. And we'll talk about why they can't be going at a constant velocity, at least in this situation, and be in equilibrium. Okay, so what are the properties that happen? Well, the first one is inside the conductor, the electric field has to be zero. This is any conductor in electrostatic equilibrium. You can immediately say, the electric field, I know it inside the conductor, it's zero. The next thing that has to be true is any excess charge, that is, any charge that isn't paired up in its atom, any free electron or little lonely nucleus that is sitting there being positive with no electron, all of that is on the surface of the conductor. And that can be the outside surface. So say this is a conductor and the electric field is inside because it's an electrostatic equilibrium. If there are any unpaired electrons, they're on the surface. If there are any unpaired nucleuses, they are also on the surface over here. But maybe you might have a cavity in this conductor. So this is the conducting material here, but this is just a hole in it. You could have some charges that are unpaired and they're on the inside. That's also on the surface of the conductor, so that's okay. You also must have that the electric field on the surface, so not inside, but right outside on the surface where all the excess charge is, that is perpendicular to the surface. So here's your conductor. Inside, the electric field is zero if we're in electrostatic equilibrium. Maybe there's some extra charge that is unpaired, not in its full atom pair here. And if there's any electric field, well, it is pointing straight out like this, normal to the surface. Which kind of makes sense because it's probably these field lines are either ending or beginning on this excess charge that's on the surface, but it definitely points out at a 90-degree angle to the surface like that. Next thing, the magnitude of this surface charge is going to be equal to the surface density, wherever you're looking on the surface, divided by epsilon naught. And remember, surface density is charge over surface area. So this charge that's on the surface divided by the surface area, and this doesn't have to be constant. You could have more charge at some part and less charge at other parts. But wherever you are looking for this particular electric field, well, the magnitude is going to be the surface charge density at that location divided by the area. All right, so these are the properties. Why must they be so? We'll start with this one. So here is our conductor. And say it's not true that the electric field inside here is 0 in our conductor. Maybe there's an electric field that points like that. All right, well remember, if you've got an electric field and you've got charge, you have an electric force. And because these charges, well, they're there, so they have Q, so when they're in an electric field, they will have a force, they can move, they will feel an acceleration. So the little electrons, because their charge is negative, they're going to feel a force opposite the electric field, and so they're going to accelerate this way, and they're going to keep going until they actually smack into the surface here. And if there are any positive nucleuses, well, their electrons are going to keep hopping until the unpaired nucleus ends up over here, and then you've got a negative charge here and a positive charge here, and that's going to create an internal field that is opposite this red field. And in fact, it's going to keep moving charge until these two are exactly the same magnitude, pointing in exactly the opposite direction, and they cancel. So you will have no electric field inside. And another simpler way to say it is if you have an electric field inside and you've got some free charges to move, you're going to have force, they're going to accelerate, charges are moving. It's not electrostatic equilibrium because things are moving, not being still. That's also why the charge has to be on the surface. Because you see, the charges kept moving until they ran into the surface. And that's also why you can have equilibrium in this case, but only if things aren't moving. Normally, equilibrium means that the net force on an object is 0. But that means just the acceleration is 0. It doesn't mean the velocity is 0. So it just means the velocity is not changing. But you can't have a charge, like an electron, with a velocity that doesn't change, because eventually it's going to smack into the surface of the conductor, and then it's not allowed to leave the conductor. Like, it's free to move inside the conductor, but it can't just like take off into space. And so the only way to get things so they are not accelerating, because they can't have constant velocity because eventually they run into the boundary, is they have to not be moving at all. And because of that, they also have to be on the surface if they're unpaired. So that's the first two. The next one, I'm going to break this one up. The electric field, when you're on the surface, is perpendicular to the surface. All right, sorry, my handwriting got really hard to read there. But let's see why this is. Here I've done a zoom in on my conductor. The electric field inside the conductor is 0. Any charge that is unpaired in its atom is out here on the surface. And let's say that's not true. Let's say there is some electric field right here on the outside on the surface that is parallel to the surface rather than perpendicular. So maybe we have an electric field which looks like this, and it'll have some component of it is perpendicular, that one, but maybe some of it is parallel, like that. And in fact, I'm not even going to write it there because the electric field inside is always 0. I'm going to write it up here. All right, so if there's a parallel component of the field, that means there's going to be a parallel component of the force. And because all of the charges up here, well, you're going to have non-zero Q, and you're going to have an E that is parallel, but now there's a force in the parallel direction as the surface, and that means any charges here can then accelerate there, and they're going to move around, and you're not in electrostatic equilibrium. And they're in fact going to move until they create an electric field that is equal to this one, but opposite in direction, and it will cancel. And then right at the surface, you'll be left with an electric field that is only perpendicular. Now, for why the magnitude of the electric field on the surface is equal to the surface charge density divided by epsilon naught, and it's in the normal or perpendicular direction, this we'll do in a later video. But it's really cool. It uses Gauss's law to show that. All right, so that is what you need to know about conductors and electrostatic equilibrium. First, the electric field right outside of the conductor is equal to this. When you are inside the when you're inside the conductor, the electric field is always 0. And if there's any excess charge, any charge that isn't bound up and paired up in an atom, it's on the surface. So excess charge on the surface of the conductor. And that's what you need to know about conductors when they're in electrostatic equilibrium.